Welcome to Programming Fluency. This is section 11.1, Debugging with GDB. Your program crashes, and you spend 20 minutes adding printf lines to hunt for the cause. In this video, you will learn a tool that finds the same bug in 30 seconds. Let's begin. Your program crashes with a segmentation fault. You add printf calls, recompile, run again, and narrow the bug down to somewhere between line 50 and line 200. 20 minutes later, you find it. In this video, you will learn a tool that finds the same bug in 30 seconds. It is called GDB, the GNU debugger. Let's get started. This is the plan for this video. First, why printf is not enough. It changes your code and it only shows what you thought to print. Next, the mental model. GDB is a pause, inspect, and resume remote control for your program. Then breakpoints and stepping. You compile with -G, then use break, run, next, and print. After that, the backtrace. It reads the chain of function calls that led to a crash. Finally, watchpoints and conditions. You pause only when a value changes or when a condition is true. You have been debugging with printf since chapter 1. For simple bugs, it works fine, but printf debugging has 3 real problems. First, you modify the program to debug it. Every printf you add changes the source, so you must recompile, and later you must remove them all. Second, you only see what you thought to print. If you did not print the variable that matters, you find the gap, add another printf, and start over. Third, some bugs vanish when you add printf, because printf changes the stack and the memory layout. These are called Heisenbugs. Observing them changes them. A debugger solves all 3 problems. It lets you pause a running program, inspect every variable, and walk through it line by line without changing a single line of source. So what is GDB? GDB stands for the GNU debugger. It is an interactive command line tool for running your program under controlled conditions. GDB lets you pause execution, inspect variables, memory, and the call stack, step through code one line at a time, and then resume, all without modifying the source. It works with C, C++, Rust, and other compiled languages, so learning it once pays off everywhere. Think of GDB as a pause and play remote control for your program. Without GDB, your program runs from main to the end, or to a crash, without ever stopping. With GDB, you place breakpoints in the code. A breakpoint is a pause marker. When execution reaches 1, GDB takes over and pauses the program. This figure shows the core loop. While paused, you inspect the whole state, every local, every global, the full call stack, and raw memory. Then you decide what to do next. Step one line, continue to the next breakpoint, or quit. Before GDB can show you variable names and source lines, it needs debug symbols. The compiler generates them when you pass the -G flag. The command is gcc-g-big O0-wall-o buggy.c. The -G flag embeds the symbol table, the variable names, and line numbers. The -big O0 flag disables optimization, so the machine code matches your source line by line. Without -G, GDB shows only assembly and raw addresses. Without -big O0, the optimizer reorders and eliminates variables, which makes stepping feel erratic. So during development, always compile with -G-big O0. This is a small program with a deliberate bug. The function SumArray loops over an array and adds up the elements, But look closely at the loop condition. It says I less than or equal to size. The array has 5 elements with valid indices 0 through 4. When I reaches 5, the condition 5 less than or equal to 5 is still true, so the loop reads array index 5, 1 past the end. Let's use GDB to find this bug without adding a single printf. Let's start a session. You type GDB, then the program name. GDB loads the executable and its debug symbols and gives you the GDB prompt. Now you set a breakpoint. Type break, then sum array. GDB confirms breakpoint 1 at buggy.c line 4. Now type run. The program executes normally until it reaches the breakpoint, then pauses and shows the current line and the arguments. So break sets a pause marker. It can take a function name, a file and line number, or just a line number. And run starts the program. It stops at the breakpoint and shows the arguments. The program is now frozen, waiting for your commands. Now step through the code. The next command runs the current line and stops at the next one. After 2 next commands, you are inside the loop body at line 6. Now use print to inspect variables. Print I shows 0. Print array index I shows 90. Print total shows 0 because it is about to be updated. So next runs the current line and stops at the next, and print shows any expression. A plain variable, an array element like array index 3, a pointer dereference like $p, or a struct field like node arrow data. This is the heart of GDB pause, then print whatever you want to see. 2 commands look similar but behave differently. Step and next. Both run the current line and stop at the next one. The difference is what happens at a function call. Step enters the call. You land inside the called function and walk through it. Next steps over the call. The function runs to completion and you stop at the next line in the current function. The simple guideline is this. Use next most of the time. Only use step when you want to enter a function that you wrote and need to debug. If you accidentally step into a library function like printf, you will be lost in hundreds of lines of library code. Rather than stepping through every iteration, use a conditional breakpoint. Type break 6 if I equals 5. This breakpoint only triggers when I is 5, the exact iteration we suspect. Then type continue. GDB runs until I is 5 and pauses. Print I confirms it is 5. Print array index 5 shows 32,767, which is garbage left on the stack past the end of the array. So break line if condition skips thousands of correct iterations and pauses only on the problematic one. There is the bug. The loop should use I less than size, not I less than or equal to size. This is the whole session as a trace table. Each row is one moment in the life of the program, showing I, array index I, and the running total. First, run stops at line 4 before the loop with total 0. After 2 next commands, we are in the loop body. I is 0, array index I is 90, and total is still 0. After the first iteration, I is 1, and total is 90. Then the conditional breakpoint fires when I is 5. Now array index 5 reads 32,767, pure garbage past the end of the array, and that garbage gets added to total. GDB also shines when your program crashes. This function finds a file extension. It calls strchr to find the dot, then returns dot plus 1. But it never checks whether strchr returned null. When the file name has no dot, strchr returns null, and evaluating dot plus 1 on that null pointer is undefined behavior, producing an invalid pointer. Run this in GDB and it crashes with a signal. Seg-v, a segmentation fault. Notice the crash happened inside strlen, deep in the C library. That is not where the real bug is. To find the real bug, you need the backtrace. Read the backtrace from the bottom to the top. Main at frame 4 called print extension with the string readme at frame 3. Print extension called printf at frame 2. Printf internally called strlen at frame 0, which crashed. So the backtrace, abbreviated BT, is the chain of function calls leading to the current point. Frame 0 is where execution stopped. Each higher frame is its caller. Even though the crash is inside the C library, the backtrace points you straight to your own code, frame 3, where the invalid pointer came from. Sometimes a value is wrong, but you do not know which line changed it. That is what a watch point is for. Type watch, then the variable name, here sum. Then type continue. GDB runs until sum changes, then pauses and shows you the old value 90, the new value 180, and the exact line that changed it. A watch point is a breakpoint that triggers whenever a variable's value changes, no matter which line changes it. Set it with watch var. Use it when you know a value is being corrupted, but you do not know where. It says hardware watch point because GDB uses a fast processor feature, so watching a value costs almost nothing. 2 common mistakes. First, forgetting -G if you compile with just gcc-o prog. GDB still runs, but it shows only assembly instructions and hexadecimal addresses. No variable names, no source lines. The fix is to always compile with -G-big O0 when you intend to debug, and to add -G to your makefile C flags. Second, confusing step in next. If you type step when you meant next, you step into printf's internal implementation, hundreds of lines of library code you do not care about. The fix is to use next for library calls. And if you do land inside a library function, type finish to run until it returns and bring you back to your own code. Let's recap. GDB replaces guesswork with direct observation. You pause the program, inspect every variable, and walk through it line by line without changing the source. Compile with -G-big O0 to get variable names and source lines. The core commands are break, run, next, and print, which drive any debugging session. The backtrace reveals the chain of function calls that led to a crash. Watchpoints catch a value changing, and conditional breakpoints pause only on the iteration that matters. And remember, use next by default, and only use step to enter a function you wrote. Next, GDB catches crashes and logic errors, but some of the worst C bugs, memory leaks, buffer overflows, and reads of uninitialized memory do not crash at all. In the next section, you will use val grind to find these invisible bugs.